आप देख लो।
ठीक है, मेरा ख्याल है स्टार्ट कर देते हैं. About 10-15 people are here, so let's start.
Okay, ji. Assalamu alaikum ji. This is Asim Loan. Thank you, Zartaj, for inviting me in today's lecture. We'll be talking about continuous random variables today. So specifically, maybe I switch to black. So continuous, wait. This is a pencil. Wait, just a minute. Okay. So continuous random variable. You can see my screen, right?
जी.
Okay. So continuous random variables, what we want to do is, I just want to briefly describe the probability density functions, probability density, sorry, maybe we start with the distribution. So probability distribution and probability density functions. So what is the difference between the PDF of a discrete random variable and the probability density function or the probability mass function for the discrete random variable? So probability density function and the probability distribution function and probability density functions. Probability density functions, the counterpart is the probability mass function, which you have already studied in the discrete random variables. So we know the probability distribution function or the cumulative distribution function. So you have this sample space. In this sample space, you have some outcome. And what a random variable does is you map this outcome through this function, and the notation is a capital alphabet. So x of delta, and you map it to some number, real number x. And then what you want to do is, if you want to look at the probability in this interval, then what you do is you go back, if this interval is B, then you go back to this event in the sample space A corresponding to A, and then you find the probability. So you find the delta i's, find the delta i's which are associated with this interval. Okay. So the interval, the event we are that we are interested, and when the sample space is uncountably infinite, then you have the continuous random variable. So the event that we are interested in is x is less than equal to delta. So you have actually dropped x of delta. So let me write x of delta just once, and then we'll drop it again. So x of delta less than equal to x is some event A. Okay, so this is the event, and obviously you know from axioms that you assign probabilities to events. So x of delta less than equal to x is the set of deltas. So this one is a set of deltas. Deltas means outcomes. Is a set of deltas, which is outcomes belonging to some sample space, such that, so this inverted epsilon is such that x, so this is such that, and this is belonging, such that x of delta is less than equal to x. So everything that is, so if this is some x, so it's a closed interval, so the x and everything here, so all the outcomes that map into here, they will give rise to this event over here, A. And you assign probability to events. So probability of A is simply the probability that x is less, normally this delta is dropped. Delta is less than, x is less than equal to x. And this, by the way, is the definition of fx of x. This x is a random variable. This x is over here. So this is up to this point x. So that's why this is a cumulative distribution function. And obviously, when you're adding, everything is positive. When you're adding by axioms 1 and 2, it's positive, and that reaches 2, it saturates at 1. So you know from your discrete discussion on Wednesday, your probability distribution for a discrete random variable is a staircase function, and this saturates to 1 for all CDFs. So for all CDFs, this will saturate to 1. This will saturate, this will always be positive. So you can't, if this is 0, you can't have a function that starts from here. Obviously, you can't have a function start from here. This is incorrect if this is 0. And you can't have a function that is going up and then going down. So this can't happen because this is a cumulative density function and a distribution function, and everything is positive. So when everything is positive, you add positive things, so it always goes up, it doesn't come down. This is for a discrete random variable, and for a discrete random variable, you are concerned with whether this is continuous from the right or the left. So this is always continuous from the right, which means at this point, let me get rid of this one. At this point, x naught, the probability fx naught is here. And this is the jump, which is the probability at the point x equals x naught. Fortunately, in the continuous random variable case, there are no jumps. There are no jumps because there is no probability at a point. There is no probability at one point. So for a pure continuous random variable, your function is going to be like this. Again, positive. So fxx is always positive, axiom 1, and then this, according to axiom 1 and 2, this saturates to 1. Okay, so this is always going to happen. However, at any point there will be no jump. So unlike the discrete case, there will be no probability at a point. So if somebody asks you what is the probability if x is a continuous random variable, what is the probability at x is equal to x naught, this is 0, right? Because fxx naught is the probability up to this point. This is the probability up to this point. Okay? So just bear this in mind that for a continuous random variable, there is the probability at the point is 0. So that's why there will be no jumps here. So this is discrete, this is continuous, and the combination of these two is the mixed. So for a mixed random variable, you may have something like this. Sorry, you may have something. So here you have jumps. So you have jumps and you have continuous part here. So this is for a mixed random variable where you can have both the flavor of a continuous and a discrete random variable. So there is an example in the notes that Dr. Zatash has already probably sent you, and you can look at the notes and you can see, okay, because of this one. So because of this jump here, you'll have something in the density function, which is known as a Dirac function, Dirac delta. Okay, so this is the probability distribution function. If you recall, the probability that x1, so this one also. So maybe if you have x less than equal to x1 is a subset of x less than equal to x2, then this by definition, if I take the probability of both sides, then obviously this will be fx of x1 because it's subset. So this will be less than equal to fx of x2. Obviously x1 is less than x2. Okay. So you have actually maybe x1 is over here, x2 is over here. So you're saying x less than equal to x1 is this portion, and x less than equal to x2 is this portion. So obviously the first one is a subset of the other. So if fx of x1, so this means this is a cumulative function and it's adding up. So you also know, okay, if I have probability of x1 less than x less than x2 from your discrete random variable case, this is fx of x2 minus fx of x1. If I say x1 is some small x and x2 is some x plus delta x, then what I have is I have probability of x less than equal to x plus delta x. By the way, also note this thing that for continuous random variable, this less than or less than equal to doesn't makes a difference. Why? Because obviously there is no probability at some point. So it's only for the discrete case when we are concerned with whether this is a less than or is a less than equal to thing. So the probability between some small interval delta x centered around x, and this one is simply fx x2, which is x plus delta x, minus fx x1, which is this one x. Okay. And if I take, say, and if I divide both sides by delta x, if I divide both sides by delta x, and then I say limit delta x tends to 0, I say limit delta x tends to 0, what is this right hand side equal to? So what is this right hand side? This is the definition of what? Anyone? This is the definition of what? This is the function at some small interval plus delta and minus the function at the point. So this is a function in some small spread over some small interval delta x. You divide by delta x, limit you take limit delta x tends to 0. This is the definition of the derivative. This is the definition of the derivative. Since this is the definition of the derivative, this is called the probability distribution density function. So this is the probability density function. This is exactly the same as a probability mass function, because this is probability. This is the probability per length. So probability in an interval divided by the length. So that is the probability mass function. That's a probability at some point. So probability density. This is called PDF. Probability density functions. And if you are familiar with, so this is small PDF, the distribution function is capital. So this one is capital PDF, and this one, the small f, is actually the small PDF. So probability density function, same. If you are familiar with the Dirac delta, let me just connect the two. If you're familiar with the Dirac delta and you have probabilities, so maybe it's a binary random variable, where you have or a Bernoulli random where you have only one, where you have both are maybe P and Q. Maybe you have, this is P and this is Q. This is some X1, this is some X2, 0 or 1, whatever you want to call them. And you say that this is actually P into delta of X minus X1 plus Q. If you are familiar with this notation, then you can tie actually both of them together. Delta of X minus X2. This is the probability density function. Okay. So for a discrete random variable, you have delta of Dirac delta function, and they are actually shown. The notation is an arrow. It's not a point. That's a Kronecker delta. So the probability density, so this is for a discrete random variable. For a continuous random variable, obviously you will not have these delta functions, but for the mixed case, wherever there is a jump, you will have a delta function. Okay. So in any case, we'll look at some discrete random variables, and we'll see how do we define those. So in any case, this probability density, since this is probability, this is positive. This is positive, axiom 1. And then from axiom 2, where this saturates, so when we said okay, this will saturate, so for the distribution function, the distribution function saturates. And where does this 1 go for the density function? So we know fx of x is d by dx of fxx, or when we integrate, or so if I integrate, we have fx of x is minus infinity to x. So this x goes here. So obviously you're accumulating from minus infinity to x. And inside here you have fx of lambda d lambda. Yeah, this is a demi variable, doesn't make a difference whether this is lambda, y, z, whatever that is. And when I say fx of infinity, so when I put x is equal to infinity, this would be from minus infinity to plus infinity, fx of lambda d lambda. Maybe I can change this lambda to x, doesn't make a difference. This is just a dummy variable. So fx of x dx, and since fx of infinity, if we go back here, fx of infinity, so this saturates to 1. So obviously fx of infinity is 1. So this is 1, and this is the normalization condition. So all density functions should integrate to 1. So normalization condition. This is the normalization condition. So this is a test. This is a check. This is a check or a test. If you have a density function and you find the area under the density function, that area should be equal to 1. So that is why probably if you are familiar with the normal or the Gaussian density function, which I'll just describe in a little while. So for the normal or Gaussian random variable, so if x is normal or Gaussian random variable, this function is like this. It's a bell curve. Okay. It's a bell curve. This is centered around some number, and we'll see what that number is. If I integrate from minus infinity to plus infinity, so this density function is this one, fx of x is 1 over sigma x root 2 pi exponent minus 1 over 2 sigma square x, x minus mean of x whole square. This is centered around eta x. This spread is sigma x, and we'll see what these numbers are. And this 1 over sigma under root 2 pi, 1 over sigma root 2 pi, this is the normalization condition. So if this is not there, this function is not going to integrate to 1. Okay, so this is the cause. And similarly, if you have an exponential random variable, if you have an exponential, which is the counterpart for the geometric random variable. So exponential random variable, if x is exponential, then you will see fx of x is actually lambda e minus lambda x. And either you write x greater or equal to 0, or you write lambda e minus lambda x, and you say u of x. This u of x is a unit step function. Same here, this lambda is the normalization condition. If you just integrate e minus lambda x, this is not going to be equal to 1. But if you integrate lambda times e minus lambda x, this will integrate to 1. Okay. And integrating, obviously, for positive, it's a positive random variable. This is a unit step. So u of x is a unit step function. It's a unit step function. And unit step function, if you're familiar with signals, this is a discontinuous function at where the argument is 0. And then it becomes a 1. So this simply means your function is only valid for when x is positive. Okay, so just to recap, your fxx has no jumps. This has no jumps. So no jumps for continuous random variables. And for the distribution function, and for the density function, this function is obviously positive. This is probabilities. And if you integrate from minus infinity to infinity, fx, whatever that range is. So in general, it's just from minus infinity to infinity. This will always be equal to 1. So these are the two checks. So whenever you have a distribution function, or whenever you are asked to find a distribution function, just make sure that these two conditions are satisfied. Okay? So once you are comfortable with these two functions, with these two definitions, which is actually the same as for the discrete case, let's move on to continuous distributions. Once we do the continuous distributions, then I'm going to do some moments. And the last thing that Dr. Litash is going to do probably on Wednesday is, for example, what he wants to do, what he'll be doing on Wednesday is, let me just give you a heads up. Suppose you have a uniform, and I'll just tell you in a little while, what is a uniform random variable? So suppose that you have a uniform. So whenever you generate a random variable in MATLAB or from your calculator, so it's a uniform random variables between 0 and 1. Okay? And suppose you want to, somebody says you want to generate coin tosses. it's equally likely heads or tails. So what you want to do is you want to transform this uniform random variable so that from instead of 0 and which is spread over 0 and 1, you have either 0 or 1. So how do you do that? This Dr. Zirtash is going to talk about on Wednesday, inshallah. So that is what is known as transformation. Or suppose if you have Gaussian random variable and somebody asks you to generate a log normal or a chi-square random variable. So how do you do that? So that is where you have transformation of a single random variable. Obviously, you can also do transformation of multiple random variables, but what you do there is you have y is equal to g of x. So you have some function g, you have x ke liye, you either have the PDF or you have the distribution or the density function. So this is given, G is given, and you have to find what is the distribution and the density function. So either you so for a random variable, either you calculate the distribution and the density function, which completely describes the random variable, or another way of describing a random variable is through some numbers, and those numbers are moments. Those numbers are moments. So we'll see in a little while by the end of today's lecture, what are moments. Okay. So this is on Wednesday, inshallah. And this is today. Okay, what are the different distributions and how do we calculate different moments and what are different moments? So there are just a couple of moments that we are interested in. For all others, you can calculate them, or actually there are just a few that you have to compute. All others are actually just to give you a complete description in terms of the density function, and I'll tell you how they are related. Actually, so continuous random variables, when the first continuous random variables, the first one is the uniform distribution. And uniform distribution is exactly the same as equally likely case. So for the discrete random variables, you must have studied the equally likely case. So this is the equally likely case. If you have absolutely no information, about the event or the experiment, you just assign uniform probabilities. If there is absolutely no information about the experiment you are performing, then the best thing is that actually this is the worst thing, that everything is uniformly, it has equal probability, and that is when you use uniform distribution. So uniform distribution is used when there is no information. So when there is no information about the experiment, then you use uniform distribution. What is uniform distribution? This is same as equally likely case. Equally likely case simply means, okay, if you have somebody say the x, so if you say x is the random variable, is uniformly distributed. You don't say uniformly densityed. So it's uniformly distributed over AB. So AB are some constants, AB, and this is X. So this is the uniform density. So this is the PDF of a uniform random variable. And obviously now, since we know this thing, we know, okay, the area has to be 1. So the area of this thing is 1 करने के लिए क्या करेंगे? So this is B minus A, since this is B minus A, and this one has to be 1 over B minus A. So this area is now 1. Okay. So Fx of X. So याद रखेंगे. So everything is equally likely. अगर आप इसमें कोई, if you want to imagine some small points, हर एक में there, so that this is everything has the same probability. So Fx of X is 1 over B minus A for A less than equal to X less than equal to B and 0 else. Yeah, so this is how you define the PDF, or this is how you define actually a uniform random variable. So this is how you define a uniform random variable. So again, yaad rakhiye, whenever whenever you have no information about the experiment, ki kya hona chahiye, so you always, so this is the worst case कि you assume that this is uniformly distributed. Okay. It's much, it's very simple. It's ये जो random variable है, it's the easiest to compute actually. The next random variable, which is the most popular one, is the normal or Gaussian random variable. So I'll do some calculations or do some examples later on in the lecture, inshallah. So normal or Gaussian random variable. So normal or Gaussian random variable, if you have studied the Laplace, De Moivre-Laplace law, I think it's the De Moivre-Laplace law, De Moivre-Laplace theorem. So in De Moivre-Laplace theorem, I think spelling bhi yahi hai. So in the De Moivre-Laplace theorem, I think you have the binomial case, you have the binomial random variable, and depending on the binomial random variable, you have actually either the Poisson distribution or you have the normal distribution. Basically, I think there's some condition on NP and N greater than P, whatever that condition is. So to calculate the binomial probabilities, which is NK probability, K tosses in N, K heads in N tosses, P, K, Q, or N minus K, or P successes, Q failures, just sort of however you want to define them. So you have the Poisson and the normal case. So normal case mein, so normal random variable, whenever you have a large number of small distributions, just like the Brownian motion, agar aapko yaad ho. So sum of a large number of small distributions. Sum of a large number of small distributions, or small disturbances, small disturbances. So if you want to take their cumulative effect, this is modeled as a Gaussian random variable. So the Brownian motion hota hai na, usme bhi you have a large number of small disturbances. Uska jagah cumulative effect, if you want to model it, then you model it as jab thermal noise hoti hai na, so your thermal noise is actually modeled by the Gaussian normal or Gaussian random variable. This is the most important random variable in all of probability theory, whether it's discrete or continuous case. So normal may, so X, it has two parameters, and I'll tell you what those two parameters are. For the time being, just assume there are two parameters. So you have this parameter eta X, either you drop X or you just keep X, and this is some sigma square X. And I'll tell you what are these two parameters. And the density function here, again, it's the probability density function through which we define these random variables. So this fx of x is 1 over sigma x root 2 pi e minus 1 over 2 sigma square x minus eta x whole square. And if I ask you to sketch it, since this is a square, so this is a square, so it's symmetric around eta x. So if you sketch it, and always try to sketch these functions. Whenever you are trying to solve problems in engineering, always sketch them. Hopefully the sketch is symmetrical. So this is x goes to infinity, goes from minus infinity up to plus infinity. This point here is some eta x, because when this x is equal to eta x, this is e raised to 0, 1. And obviously this height is 1 over sigma x root 2 pi. Okay. So this is fx of x. Again, if I want to find some area up to this point, if I want to find this area, maybe I say x naught. So this area is simply minus infinity up to x naught, fx x dx, which is equal to, so this is what this area is. This is what this area is. And this is from minus infinity to x naught, 1 over sigma x root 2 pi e minus 1 over 2 sigma square x minus eta x whole squared dx. This is a big no-no. If I ask you to calculate a b e minus x squared over 2 dx, kindly don't say that this is equal to, don't say that this is equal to e minus x squared over 2 over minus x a to b. This is not equal to this one. This is not equal to this one. So there are some intake functions which you cannot analytically integrate, evaluate, and you have to do normal integration. This is one such function. So there are tables to find what is this area. Please do not say e of minus x squared over 2 when integrated from a to b is actually equal to e minus x squared over 2. The exponent here is minus 2x. 2 se cancel, so minus x karke you integrate from a to b. This is a big no. Please do not say that. So this is not correct, so don't do that. So you always need to have some tables, और उसके लिए tables के लिए there is a unit normal variate. This is exactly the same as when you generate the uniform distribution, you say कि your number is between 0 and 1. इसका मतलब you can always transform 0 or 1 की जगह this number is between some a and b. ठीक है, तो उसके लिए you'll see on Wednesday inshallah how do you transform from 0 and 1 to a and b range में. तो उसके लिए, so similar to that there is something known as unit normal variate. Unit normal variate. By the way, ये बताएं कि is this function even or odd? Is this function even or odd?
Even.
No. Why is it even? This eta x is not equal to 0. मैंने तो कोई लिखा नहीं कि eta x is equal to 0. This function is not even or odd depending on eta x. If eta x is 0, then it's even. Otherwise, it's not even. तो याद रखें कि just देखें ना, I can draw a 0 line इधर भी बना सकता हूँ. So this is actually, if eta x is not equal to 0, then this function is not even. It's not an even function. Just bear this in mind. So similarly, but this one, the one I am defining, so unit normal variate. So unit normal variate के लिए, you have x not. So this is the notation actually for the normal random variable. The first parameter here is 0 and the second parameter is 1. So just bear with me for a little while and then I'll tell you what are these two numbers. So x, 0 and 1. So 0 is eta x and 1 is sigma square x. And now this function is even. This is 1 over under root 2 pi because sigma square is 1 and obviously sigma square is 1, so sigma is 1, 2. This is fx of x and this function is fx of x is 1 over 2 pi e minus it's gonna actually sometimes books आपकी ना they use x की जगह z use करते हैं. इस one कोई फर्क नहीं पड़ता. E minus x squared 2. There is no u of x here. Why? Because x goes from minus infinity to plus infinity. Okay, so Gaussian function की जो range है, this goes from minus infinity to plus infinity. So now if I if this is some z कर लेते इसको सर. So if this is some z and I want to find this area, okay, so if I want to find this area, so this area is actually from minus infinity to z e minus x squared over 2 dx divided by root 2 pi. There are different functions. So this is actually by definition, this is the distribution function up to the point z. This is a distribution function up to the point z. But आपके पास then there are other functions. जिसमें there is an ERF function. It's an ERF function, or there is an ERF complement function. Yeah, you look up in your Excel or your MATLAB, and then there is ERF. Maybe I write ERF of z. So ERF of z or ERF complement of z, or there is something also known as Q of z. This is the Gaussian tail function. This is the Gaussian tail function. If you have done some communication taken a course on communication in your undergraduate, then you would see, अच्छा, अब ये जो fx of z है, this is from minus infinity up to this point. इसका मतलब ये वाला जो point है, ये वाला जो portion है, which maybe I do this thing. So if for this portion, this is simply 1 minus fx of e, right? This portion is simply 1 minus fx of z. So this is 1 minus fx of z, because obviously the area integrates to 1. So if up to this point is fx of z, so this yellow highlighted is simply 1 minus fx of z. But this portion can also be written in terms of this Gaussian tail function, because this is the tail of the function. So q of z is actually z to infinity, from here to here, z to infinity. And so this z actually goes here. Okay, so just fx of z में this z goes in the top इसके limit के अंदर. So q of z is from z to infinity 1 over root 2 pi e minus x square over 2 dx. And by the way, whenever you are integrating, what you can always do is you can always do a change of variable here. आप ये कहेंगे ना कि how is this related to this one? उसके लिए it's much simpler. So let me write it here. Just so that you don't get confused. This is 1 over sigma x under root 2 pi. Suppose you are asked to do calculate a to b. जो a to b means somewhere here, a to b. Okay, so इसको a कर लें, इसको b कर लें. So if you want to integrate from a to b, what you want to do is a to b, and this is not normal, for example. Okay, suppose you have this function 2 sigma square x minus eta x whole square dx, and you have to integrate in terms of ये वाला जो function है, ये जो आपके base. Sometimes ना इसको g of x भी कह देते हैं. In some books this is g of x, depending on आप कौन सी text इसको you're following for this course. To convert from here to here, you say let, so this is simply a change of variables. So this is simply let x minus eta x over sigma x equals, let's say, some y, then dx over sigma x would be equal to dy. Okay? If I do a change of variables here, so obviously x minus eta x over sigma square, this will be e minus y square over 2. Okay? Dx over sigma x would be dy. When x is equal to a, this will become a minus eta x over sigma x. And when x is equal to b, this will become b minus eta x over sigma x, right? And this, by the way, is actually fx. So maybe I show you this one. So this is simply from here up to this point minus from here up to this point. Okay? So first is yahan tak sara, everything here, and from here then you subtract everything here. So this is what you'll be left with. So yeah, this is equal to, following this notation, fx. So this is upper limit, or maybe I write it like this. This is from minus infinity to b minus eta x over sigma x e minus y square over 2. And there is under root 2 pi over here too. Under root 2 pi dy minus infinity a minus eta x over sigma x e minus y square over 2 root 2 pi dy. And this is simply equal to fx or g, upper limit here, b minus eta x over sigma x minus fx a minus eta x over sigma x. Obviously, there are tables available. Either you use tables or you use your MATLAB or Excel. So Excel, MATLAB or Excel आप use कर लें. So you'll find these ERF and ERF complement. Obviously, you look at the definition. Just see how they have defined. Have they defined it like this, or they have defined there is under root 2 pi and there is a 0 here instead of a minus infinity. Usko you can always do a change of variables, and then you will see actually this is how you will integrate. So this is the function. This is the area between A and B. So if this is A, this is B, this function is actually, this area is this one. Okay, so this is how you do a change of variable for the Gaussian case, and then you figure out ये किस तरह चीज होती है. अगर अच्छा, I don't want to tell you कि जिस तरह वो कहते हैं ना within 1 sigma x or within 2 sigma x, since I have not told you what is sigma x, so I don't want to tell you कि within 1 sigma x. So if you go to your text, probably you should find something like this. उसमें यूं होगा कि if this is within 1 standard deviation, within 2 standard deviations, or and so on and so forth. Within 3 standard deviation, I think 99.9% of the area is within plus minus 3 sigma x. Okay. Actually, I've told you what is sigma x. Actually, the third distribution that I want to talk about is the gamma, and related distributions. There are 2 of these which are important. Gamma and related distributions. And the density function for the gamma function is fx of x is some lambda. So this is a function of, there are 2 parameters that define these. That's why this is a family of functions, family of distributions. Gamma raised to power eta divided by, lambda raised to power eta, gamma of eta, x raised to the power, this is x raised to power eta minus 1, e minus lambda x, and this is x, e minus lambda x, and this is for x greater or equal to 0. So again, instead of x greater or equal to 0, I can always write u of x. Because this is a unit step function. Both lambda and eta are positive. Both lambda and eta are positive. Lambda is called the scale parameter. This is the scale parameter. And eta is the shaping parameter. This is the determines the shape of distribution. Determines shape of distribution. These are unimodal. Unimodal, there is only one peak. Unimodal implies one peak. So, and we can have a wide variety of these functions for different lambdas and different etas. So one of them is when eta is 1. So when eta is 1, fx of x is simply lambda. What is this gamma function? So gamma function is defined like this. So gamma of eta. So whenever you put a triangle on top of an equal to sign, this is a definition. This is 0 to infinity u of eta minus 1 e minus u du. So this is the definition of a gamma function. Or gamma function k, and then you can have gamma function of half is under root pi. Gamma function of z plus 1 is z times gamma z when this z is not an integer, and this is also equal to z factorial if z belongs to a set of integers. Okay, so from all these 3 definitions values, you can actually find gamma, the value of gamma of eta for any value. Okay, and this for z greater than 0. So if eta is equal to 1, what is gamma of eta? Gamma of 1 is z is equal to 0 factorial. 0 factorial is 1. So this is 1. So gamma of 0 is 0 factorial, which is 1. So 1 in the denominator, eta is 1. So 1 minus 1 is 0. X raised to power 0 is 1. And we have e minus lambda x. And from with here, we have x greater or equal to 0. This is an exponential random variable. Which is its counterpart is the geometric random variable. So it's the geometric random variable, which geometric random variable has memoryless property. Exponential has also the memoryless properties. And you'll see that this also has the memory. So where is this exponential random variable used? This is actually models this models inter-arrival time between in a Poisson process. When the arrivals are Poisson, then the time between the arrivals is actually modeled as an exponential random variable. Okay. Models inter-arrival time when arrivals have a Poisson distribution. When arrivals have a Poisson distribution. और इसके लिए मैं आपको जल्दी से I'll just give you why are we saying that this is inter-arrival time is exponentially model. उसके लिए यूं देखें कि let x be the number of arrivals, in this interval 0, t, in 0, t, and assume let x be the number of arrivals in 0, t via a Poisson distribution. So the time between two successive arrivals is also a random variables. Between two successive arrivals, t is also a random variable. This is also a random variable. Then I can define this distribution. Ft of t is simply the probability that t is less than equal to t. Okay, this is by definition. T is less than equal to t, which is simply equal to 1 minus probability t greater than t. Why? Because these two are disjoint sets. दोनों को add करेंगे. When you take the union, this should add up to 1. Okay? And this is for t greater equal to 0, 0 else. So in terms of x, what is this event equal to? T greater than t. इसका क्या मतलब होगा? In terms of x, t greater than t. T is the time between two successive arrivals. T is the time between two successive arrivals, and x is the number of arrivals in 0 to t. So if this t is greater than t, what is this in terms of x? So this implies x is equal to what? When t is greater than t, इसका मतलब जो arrivals are happening between 0 and t ना. So if t is greater than t, this means there is no arrival in this interval. ठीक है ना? So this implies no arrival in 0 to t. If there is no arrival in 0 to t, this implies, since x is the number of arrivals, this means the x is equal to 0. But what is the probability x is equal to 0 if the arrivals obey a Poisson distribution? Then this is simply क्या होती है e minus lambda t. क्या होता है lambda t k factorial होता है k is 0 ना. So k is 0 here. Since k is equal to 0, this is simply e minus lambda t, or this implies f tt is 1 minus this thing. ये चीज है 1 minus e minus lambda t. And if I take the derivative over here, which is d by dt of f tt, this is simply lambda e minus lambda t. Okay? And obviously there is a u of t over here too, and there is a u of t over here too. So this and this is exponential, and this is what we said, okay, the inter-arrival time is exponential, and this is the mean arrival rate associated with. So this lambda is the mean arrival rate. I think by the end of this course, आप ये पढ़ रहे होंगे इसको चीज को. Mean arrival rate associated with Poisson arrivals. Okay. So one of the gamma distributions is important. One of the One of the members of the gamma distribution family is the exponential, and the second one is the exponential, and the second one is the chi-square. The second one is the chi-square one. So second one is the chi-square distribution. इसको I think यूं कुछ x कहते हैं, इससे chi जो भी होता है इसको Greek letter है, it's a chi-square distribution. So whenever you want to fit, whenever, so suppose करें कि you gather some data, और इसका जो most statistics में is the most famous test is the chi-square test. So if you get some data and you want to fit and you want to see that this data can be modeled as which random variables, so the best thing is, because chi-square जो chi-square test होता है उसमें the chi-square random variable has a lot of parameters. तो उसमें you can actually play with the parameters and then see which one fits the best model आपके जो data को होता है. So that is where this chi-square test is used. So chi-square distribution, whenever you have square Gaussian random variables, आप उसको square, whenever you square the Gaussian random variable, you will get a chi-square random variable. उनको add भी करने फिर भी you will get a chi-square random variable. So chi-square distribution के लिए your lambda is half and your eta is n by 2. So n actually tells you gives you the degree of freedom. So n is a positive integer. N is a positive integer. उसी density में जब आप इसको change करेंगे, so your f(x) of x, इसको याद रखने की जरूरत नहीं है, थोड़ी सी मुश्किल ही है. So it's 1 over 2. It's 1 over 2 n by 2. 1 over 2 n by 2 gamma of n by 2. This n is positive integer and is called the degrees of freedom. Degrees of freedom. So you can fit a lot of functions using different values of n. X n by 2 minus 1 e minus x by 2. Again, x is positive. This is x. This is not n of anything else. X. Okay. So sum of squares. Square कर लें या sum of square कर लें, you'll always get the chi-square one. Sum of squares of n independent. You don't know what independent is unless you study joint random variables के ये independent क्या होता है, and independent unit normal variates. This will give you, so chi-square distribution is actually sum of squares of n independent normal variables, or whenever you want to fit some data. So statistical inference में statistical inference and hypothesis testing के अंदर आप इसको use करते हो. Hypothesis testing में you use. And when you study the multiple random variables case, you will also study the central limit theorem. Central limit theorem is actually one of the most powerful theorems. So वो आपको ये कहता है, as long as you have sum of independent random variables and their mean and variance. I'll just tell you what is the mean and the variance. If the mean and the variance of independent random variables is finite, doesn't matter कि वो कौन सी distribution है, when you add them up, they will always tend to a normal random variable. That's why Gaussian random variable is so important, because you can model everything as Gaussian. Obviously, Gaussian is not as simple as the uniform one, but uniform उधर model करें when you have absolutely no information about the experiment. जब आपको पता ही ना हो, you always model it using the Gaussian normal random uniform random variable. And when you know that your effect is due to a sum of a large number of small disturbances, sum of small result of a sum of random variables, and as long as the mean and the variances are finite, then you can always model it as a Gaussian random variable. अच्छा जी, these three are actually probably the most important ones जो आप इसको कर सकते हैं, you want to use them. And now let me tell you what are moments. So let me tell you what are moments. Moments, I believe you have already studied what are moments for a discrete random variable. मैं उसी को extend कर दूंगा ताकि you know कि what is the moment for here. अच्छा, अब your PDF, the cumulative density function, distribution function, and your probability density function, they completely describe a random variable. They completely describe random variable. This is not an easy task to do. So this is not an easy, unless you are given the distribution or the density function, then it's fine. But sometimes it's much easier because you have some numbers. You have some numbers and you use those numbers to describe the random variable. So some numbers can be used to, not completely, some cases mein completely bhi ho jayega, can be used to describe random variables. Let me tell you कि इसका definition क्या होती है. So moments के लिए, and moments are those numbers, some numbers, and what are those numbers? These are moments. E is an expectation operator. So whenever you take expectation, you are actually taking out the randomness. Okay? So E of, so this is an expectation operator. So E of G of X by definition is minus infinity to plus infinity. This function G of X, okay, so this function as is, so this is some function of a random variable. So G of X obviously, G is some function and G of X is the function of a random variable. So this is the function of a random variable. So function of a random variable. Since this random variable is X, since the random variable is X, the density of X dx. Okay? So just keep this information in mind. And now let me tell you, okay, suppose recall करें. So recall for a discrete random variable, your probability mass function is like this. So if you know the direct delta notation, this is simply I probability X equals some xi. So this is a probability mass, okay, at, and this is at X is equal to xi. Okay, so this is like, okay, you have probability X equals x1. This is x1, and this one is x2. This is probability X equals x2. Okay, and this is your probability mass function. So either you have probability at x1 or you have probability at x is equal to x2. That's it. So maybe x1 is 0, x2 is 1, and you have the binary a random variable or the Bernoulli random variable. जो मर्जी आप सकते. So if you have this function, अगर आपको याद करें, and what is the mean here? अगर आपको याद हो, you said that the mean is mean is the center of gravity. अगर आपको याद हो, mean is the center of gravity, so or mean is the average. So you said कि जी take this one, this weight. इसको समझ लेना कि this is, suppose कर लेंगे, this is like your meter rule. if you're familiar with that physics experiment, जिसमें आप you have a meter rule और उसके ऊपर ना you want to find where is the center of gravity here. So what you do is you tie some weight here, you tie some weight here, and then you say कि जी ये balance हो गया, so that is where the center of gravity is. इसी तरह करते थे. So this weight is actually this probability. This weight, these weights are the probability. और ये जो distance है, this distance is actually this distance from here, x, जो distance from the center of gravity. ठीक है? इसको if I plug this one in here, तो यह क्या आ जाएगा? This will become g of xi times the probability of x is equal to xi, और ये summation आ जाएगी everything, because delta function का जो है this integrates to 1. अगर आपको delta function नहीं पता तो let me tell you, if this is some delta of x minus x naught, ठीक है, this is x naught, और इस एरिया को let's, so this is the area, this is the area, this is not the height, this is not the height. Direct delta के लिए this is the area, for chronicle delta this is the height, this is x, and this is a generalized function. The generalized function is defined in terms of its properties. So you say minus infinity to plus infinity, minus infinity to plus infinity delta of x minus x naught a, because a is a constant, dx, this will be equal to a. Okay, अगर इस a को 1 कर लें, then this is a unit impulse. So wherever this argument is 0, that is where this impulse acts. Okay, so this is simply telling you that this value is at x1, this value is at x2, and so on and so forth. So just keep this information in. So isko yaad rakhe, and when you plug this one in here, and when you assume g of x, so if g of x is, or maybe I write this. So if g of x is simply x, so यहाँ आपके पास क्या value आ जाएगी? You'll get xi into probability of xi. So then you'll get expected of x is simply I xi into probability of x equals xi. यही हो जाएगा ना आपके पास यहाँ. इसकी जगह x, क्योंकि जो integral है, this integral इसके अंदर जाएगा, तो integral integrates to 1. So you'll be simply left with xi into xi. ये इस तरह होता है. Suppose करेंगे you have this function. This function is delta of x minus xi. This function is some f of x. कोई function f of x. This is some xi. When you are integrating from minus infinity to infinity, this impulse acts only at this point. This is the only value that you'll get, f of xi. So minus infinity to infinity, f of x multiplied by delta of x minus xi d of x. ये कौन सा theorem है? This is simply equal to f of xi, because this function is only this value. This value job of integrating from minus infinity to infinity, you'll be left with this one. This is called the sifting theorem. It's not the shifting, it's the sifting theorem. और इसके लिए यूं देखें कि if you have a sieve, अगर आपके पास ये sieve है, इसमें holes हैं यहाँ, there are holes here. So जहाँ भी hole होगा, that is the one that drops through. And this is what is happening, just where the impulse is acting. This is assume this is the hole. So obviously, if this is the hole, so this is the value that will drop through. So when you plug it in here, इसके साथ, so this is what you're going to get, xi into probability of x is equal to xi. Or if you recall from your discrete random variable case, this is the mean or average, or this is the center of gravity. This is the center of gravity, and that is what this thing is. ये वाला जो हमने physics experiment किया था, ये weight है. This is the probability. This is the distance from the weight to the point जहाँ center of gravity है. And same here, ये जो दो cases हैं. And then if you calculate this thing, then this will balance out, and this is why this is called the center of gravity. So let's go back and let me write it again. So expected of g of x is equal to minus infinity to infinity g of x f x of x dx. This is the definition. If g of x is x raised to the power n, okay, x raised to the power n, this implies expected of x n is simply minus infinity to plus infinity x raised to the power n f x of x dx. This is called the nth. This is called the nth non-central moment. Nth non-central moment. If this is the nth non-central moment, m1 is expected of x. This is the mean. So the first non-central moment is the mean. M2 is expected of x squared. This is mean squared. And this is the second moment, sorry. This is the mean, or this is the first moment, first non-central moment. Non-central moment, and this is the second non-central moment. This is second non-central moment. this is not equal to expected of x whole square. ये इसके बराबर नहीं है. This is different. This is the square of the mean. This is the mean. This is the mean of the square. This is the mean of the square. This is the square of the mean. ये दोनों फर्क होते हैं. They are not the same. अच्छा. So if g of x is x of n, इसके अलावा कोई जरूरत नहीं है. Then you have the third moment, the fourth moment, and so on. But these are the first two are actually the most important one. So when you study random processes, you are going to see that the second moment is actually the one that gives you the power. So that gives you the power of the random process. Okay. अच्छा. So इसका मतलब जो ये वाला चीज था m1, this was eta x in normal. So in the normal random variable, this m1 is actually the mean. Okay, because that is where this is centered. If g of x is centered around some number, suppose Karan, this is centered around x minus m1 n. This is, so if g of x is like this, so if here, so this implies expected of x minus m1 n is by definition minus infinity to infinity. This function as is x minus m1 whole n, and then the density function of x dx, because this the random variable is x. This is called mu n, and this is the nth. This is the nth central moment. Why it's nth central moment? Why? Because it's centered around. This is, you are measuring the different dispersion. You are measuring the dispersion around the mean. Okay, so this is the mean. That's why it's called central. अगर कोई और होगा तो then it's not. तो mean के लिए इसको central कहते हैं. So nth central moment, mu of 1 is actually expected of x minus m1. And what is this equal to? याद रखें कि your expectation is a linear operator. This is a linear operator. क्योंकि अगर आप इसके ऊपर, if you go back to this definition, अगर इस g of x की जगह I have, so इसमें यूं देख लें, if g of x is some summation of gi of x, if this is g of x, then expected of g of x is actually summation of expected of gi of x. और उसके लिए, because integral is by itself is a linear operator, so this is simply sum of expectation. So if you do that here, this is simply expected of x minus expected of m1. And what is expected of m1? याद रखिए, whenever you take expectation, whenever you are taking expectation, this is a constant. So whenever you take expectation, you are removing the randomness. So whenever you're taking the expectation, you are removing the randomness. When you remove the randomness, or obviously वो एक constant number आ जाएगा. So what is expected of m1? याद रखिए, m1 is a constant. If this is a constant, then by definition, this is minus infinity to infinity m1 density function here into dx. Since m1 is a constant, goes out, this is m1 minus infinity to infinity fx of x dx. This by definition is 1 because it's the area under the function, and this is m1. So expectation of a constant is a constant. Obviously, अगर आप expectation एक randomness है ही नहीं उसमें, तो whenever you are taking an expectation, so you are going to get back the constant. So mu1 is obviously 0 because this is m1, this is minus, and so this is not of use to us. Mu1 is not important. Mu2 is actually expectation of x minus m1 whole square. Isko when I expand it, this will become expected of x square plus m1 square. So it's a minus b whole square. So a square plus b square minus 2ab. And when I expand this one, because expectation is a linear operator, this will be expectation of x square plus expectation of m1 square minus 2m1 into expectation of x. Okay, and this one is m2, this is m1 square, and this is minus 2m1, and this is also m1. So this minus 2m1 square, so this is m2 minus m1 square. This, by the way, is called the variance. This is called the variance of x. This is always positive, obviously, because this is a square. and the positive square root of variance is called standard deviation. This is called the standard deviation. This is called the standard deviation. Okay, so mu n actually tells you what is the spread. So if you recall the Gaussian case, this is the mean and this is the spread around the mean. Okay, so this is the spread around the mean. So this is the standard deviation, this is the mean. So this is the mean and this is the standard deviation. Standard deviation. One last function before we end. What happens if g of x is some complex function j omega x? So if g of x is some complex x, j omega x, then expected of g of x is minus infinity to plus infinity e j omega x. Again, it's this function here times the density function of x dx. What is this function? So don't get confused कि इधर यहाँ minus नहीं है या plus नहीं है. So that's up to us. How do we define this one? If you recall this one, this is simply the Fourier transform. This is the Fourier transform, or this is the Fourier transform of which आप recall करें ना? If you recall, if you have some f of t होता था ना, f of t, you take the Fourier transform f of j omega, जो भी notation आपने use की हुई है, तो f of j omega is actually, because it's going to be a function of omega, you are integrating over x, so you're going to get a function of omega. So minus infinity to infinity f of t e minus j, क्या होता था, e minus j omega t dt. Okay, so this is f of t, this is f of x. वो मैंने कहा this is minus, so forget about their minus है कि यहाँ नहीं है. This is j omega t, this is j omega t, t is x actually इन दोनों में. So this function is actually phi x of omega. You don't write j omega here. इधर आप लिख देते हैं, but you don't write j omega over here. This is called the characteristic function. This is called the characteristic function. So this is the characteristic function of random variable x. Or इसके जो, so this is actually, so you can always say that this and the density function are a Fourier transform pair. So if you know the characteristic function, और याद रखेंगे there is a minus का मसला है यहाँ, so you just need to be careful about the minus, the negative sign here. So the characteristic function and the density function are a Fourier transform pair. Okay, this is the most important result this lecture make. These are the, so if these are, this is a, it's a Fourier transform pair. So let me end here. So if this is e j omega x, this is phi x of omega. If I take the derivative of both sides with respect to omega, if I take the derivative of both sides with respect to omega, what do I have? So I have expected of d by d omega of e j omega x, and this is equal to expected of, maybe you write parenthesis here. So this is equal to j omega. So just jx, because when I, so it's e j omega x into jx, right? Because when I taking the derivative of this one, so it's this function as is, and then the derivative of the exponent. If I do that, and then, so this is once. What if I take it n times? If I take it n times, so I'll always get this function times j n and x, right? I'll always get this one. So this implies, so this one is phi x. So notation में ये यूं होगा, right? So this one is actually equal to this one, and this is equal to jn is a constant, expected of xn into e j omega x. And what if I evaluate this at omega is equal to 0? What if I evaluate this at omega is equal to 0? So this will become jn expected of xn, which is equal to m jn into mn. So इसका मतलब ये है कि if you want to find if you want to find the nth moment, either you do minus infinity to infinity x n fx of x dx, or you do minus infinity to, sorry, or you do 1 over jn phi x, find the nth derivative here, omega, and then evaluate this omega is equal to 0. So either if you want to find the nth non-central moment, and obviously when you find the non-central moment, you can always find the central moment from here. When you find the nth non-central moment, so you can either do the integration if you want to do the density, or if you know the density, you can find the Fourier transform pair, find the characteristic function, and simply keep on differentiating the characteristic function, whether you want to find the first, the second, the third, or whichever moment you want to find. Then you can take the derivative there and evaluate that at omega is equal to 0. I think I've run out of time, but in any case, if you have any questions, you can always ask either Dr. Zirtash, or you can send me an email, and I'll be glad to help you out. And this is my email. Okay, Ji. Are there any questions in this lecture? No? मेरे स्टूडेंट्स के साथ भी ऐसे ही होता है, they are all just quiet, कोई फर्क नहीं पड़ता. अच्छा जी, thank you जी.
तो आसिम thank you very much. तो काफी मटेरियल कवर हो गया, अभी इसको सिंक इन करने में इनको थोड़ा सा टाइम लगेगा.
कोई मसला नहीं.
Yeah. So I will share the notes, guys. I will share the notes with you. I have not yet, but I will share the notes for this material, maybe later today or sometimes tomorrow.
Okay, ji, thank you.
Challenge, thank you. Okay, ji, Khuda Hafiz.